Today we're going to start an entire chapter on mass transfer. But before that, I wanted to tie up some loose ends related to heat transfer and a brief comment on different coordinate systems. Suppose we have the governing equation for the heat equation that we'd like to solve in a different coordinate system, for example, along a cylindrical coordinate system or a spherical coordinate system. The governing equation does not change at all for any geometry that you have, rectangular coordinates, cylindrical, spherical, they all stay in this form. The difference comes in when you actually write down the form of the Laplacian. The Laplacian operator takes on different forms depending on your geometry in different coordinate systems. But overall, nothing really changes. The overall procedure of how you would solve it stays the same. I just wrote down a set of instructions on tackling these types of problems. And it turns out with different geometries or different coordinate systems, the overall procedure doesn't change at all. So you just apply what we've been doing all along for the last several lectures. First, you split up the problem if you identify a non-homogeneous boundary condition. In that case, you have to split apart the steady state, the transient part of the solution to remove the non-homogeneous boundary conditions onto the steady problem. Again, that's true for any geometry. Step 2, you guess that separation of variables will work. So you separate the time-dependent part from the spatial parts of the problem, and that spatial part might be x, y, and z. It might be r, theta, and phi. It might be other coordinate systems and their variables and their independent variables in different coordinate systems. You plug in your form of your separation guess into your PDE, which in this case would be here. You apply the right Laplacian corresponding to the particular geometry and coordinate system that you are working with. Then that will divide the PDE into multiple ODEs, one for time and each for your spatial variables. This is a step where you have to think carefully about the positive or minus sign of lambda squared, where you separate the different independent variables. And you want to think carefully which direction you want to expand in your Fourier basis function. Sines, cosines. If you're working with cylindrical coordinate geometries, you'll get Bessel's functions, Jn, Yn's. If you're working with Legendre polynomials, P sub n, there are many more functions that are just like sines and cosines that are orthogonal. So the key point is that they are orthogonal functions. And a lot of times they're called orthogonal basis functions or orthogonal eigenfunctions. Okay, so you want to think carefully about what you get here. So this is the point where different coordinate systems would yield different solutions in your spatial dimension. So for rectangular coordinate systems, you got sines and cosines for your x, y, and z. If you were to use cylindrical, you'd get your cylindrical Bessel's function. In spherical coordinate, you get your spherical Bessel's function. Legendre polynomials might come about when you solve your angular problem, etc. And there are many more orthogonal basis functions, but this is where the different geometries will come into play. So you just swap your sines and cosines with a different function like the Bessel's function. Next, you apply your boundary condition to obtain your constants of integration. Usually you obtain one of them or multiple of them. You get one for free by using the x equal to 0 or y equals 0, r equals 0. One of the 0 position boundary conditions allows you to eliminate one of the boundary conditions for free. The other boundary condition you generally use to obtain your eigenvalues corresponding to the particular basis function that you used or eigenfunction that you used. Next, you identify in stage 4 that there are many, many possible solutions for many integer values of your mode n that can satisfy the governing equation and one of your boundary conditions. Therefore, you invoke superposition and saying, well, I have many solutions that can work. To get the most general solution, I'm going to add them together. So you get your general linear solution where you superimpose all of your weights and coefficients and all of your basis functions for index n. Next, you apply your initial condition, and by this point, you should only have one constant of integration, one unknown parameter left over in your solution. You use orthogonality because sines and cosines, Bessel's functions, Legendre polynomials, cylindrical, spherical Bessel's function, they're all orthogonal functions, and therefore you can obtain orthogonality and use your Fourier coefficients at the end. And step number 7, you obtain your solution. You're all done. So really, the overall procedure, this is what we've been doing all along for 1D heat transfer, 2D heat transfer. It's true for any coordinate system, whether you have a sphere, a cylindrical rod, a rectangular slab. The overall procedure is the same. The details change when you actually get your ODE because your solution to the ODE would change depending on which Laplacian coordinate system that you're using. Okay, one more small comment I wanted to make that is related to what I talked about here. Throughout this course, I've been casually using words like eigenvalues, eigenfunctions. Let me clarify that by mapping it back to a course that you've probably taken already on vector calculus and vectors. Some of you might have been wondering over the last couple of lectures, what are you talking about? Eigenvalues, eigenfunctions, what? It just sounds like a very fancy way to call a constant. Well, let me map it back to a course that you've probably taken before, linear algebra or vectors. So, in your linear algebra class, you probably learned a form that looks something like this. You have some matrix A. I'm denoting my matrix as 2 lines underneath because it's a 2D matrix, dotted into a vector, just a 1D matrix or a vector, is equal to some scalar quantity, lambda, times the vector itself. So this form is already written in the form of an eigenvalue and an eigenvector. So this I'm sure you've seen before. The lambda is the definition of the eigenvalue when written this way, and your x's are your eigenvectors. Okay, so this you've seen before, so now you kind of know what it is. You can look at properties of your A matrix and actually obtain the different eigenvalues, etc., right? It turns out that functions can also have a very similar mapping to what we're talking about here. The only difference is that we no longer have a vector x, but it's some function, the function you want to obtain. Temperature profile, concentration profile, velocity profile, f. The A matrix is replaced by an operator. In this case, it's an operator, the Laplacian operator. So the Laplacian operator can act on some function, and if it is equal to a scalar times the same function, then f is called an eigenfunction, just like eigenvectors, but in function form. And lambda is called the eigenvalue, just like that. So f are the eigenvalues that we're talking about here. Earlier I said it's the function you want. It's actually really the part of the function that you want, which contains sines, cosines, Bessel's functions, Legendre polynomials, etc. Because look at it. If you were to stick in sine lambda x here, so if f were equal to sine lambda x, you take 2 derivatives of that, the lambda would pop outside. You'd get a negative sign when you take the cosine. Let's not worry about that. Basically, you get the same function back again as itself. So you get some operator acting on sine, you get a constant popping outside equal to the same function itself. Therefore, this lambda is an eigenvalue, and this sine function is an eigenfunction. Okay? I don't want you to take this too literally, right? This lambda, so you'd get a lambda squared. This is kind of saying that you get some scalar constant to pop outside of your function. Okay, so it's just a mapping that we're doing here. So same is true if you were to take your Bessel's function, your j sub n, y sub n, Legendre polynomial. Orthogonal basis functions will all satisfy this property of some Laplacian operator acting on your orthogonal basis function is equal to the eigenvalue of some scalar times the function itself. Notice that exponentials also satisfy this relationship. So if your functions were exponentials, which interestingly is what you would get if you made the wrong sign here of your plus or minus lambda squared. So if you make the wrong sign here and you don't get the orthogonal basis functions, you'd end up with exponentials here, sinh and cosh, the modified Bessel's function, etc. So you get the counterpart version, which is not orthogonal. But this still satisfies this relationship. You take two gradients of this exponential, you'll get a lambda squared to pop outside, and it will be equal to this generic form. Okay? So what's key is that these are both eigenfunctions. So exponentials and sines are both eigenfunctions because they satisfy this relationship, but they're not orthogonal. That's the key point. Exponentials are not orthogonal functions. You can't integrate this times itself, integrate from negative L to L, and that being 0 for all cases other than when m and n are the same. That whole property of orthogonality is only true for these functions over here. So it's not so much of the eigenfunction that's really unique. I mean, that's unique too, but for the Fourier series to work out, it's really this orthogonality that's critical. So hopefully that clears up some question about, WTF about eigenfunctions, eigenvalues, what the heck is going on? So hopefully this mapping to what you've already seen before with linear algebra space helps a little bit with understanding what we're saying with orthogonal basis functions and eigenfunctions, eigenvalues. Okay, cool. Well, let's get on to the main subject of today, which is transition over to mass transfer, which is an incredibly important subject for physics, chemistry, biology, all fields. So let's get started with mass transfer. Today, let's consider mass transfer. We've done a lot so far about how energy flows from one place to another over space and time. But as scientists and engineers, we're not gonna only want to know how energy transfers from one place to another. A lot of species and mass and material, physical material transports from one place to another. That is called mass transfer. And we want to derive an equation, a governing equation, like the heat equation, that allows us to figure out how materials and mass and chemical species moves as a function of position and time. Now we're going to go back to our favorite derivation using a shell balance. Recall several lectures ago when we derived the heat equation using a shell balance, a geometry that looked just like this, where we had a material, we cut out a small little cross section, a small little piece of thickness dx, and we conserved the energy inside that slab. Both heat coming in, heat coming out, the accumulation plus generation occurring inside that small little differential volume element. Now let's first consider the heat flux, or in this case, the mass flux, because that was a key term that helped us make progress in this problem. In the heat flux, we use this relation called the Fourier's constitutive relation. And it looked something like this. All right, so for Fourier's relation, we wrote it this way. The heat flux is equal to the thermal conductivity K, a material property, times the temperature gradient inside that material, with a negative sign out in front due to the sign convention. Now focus on the units of the heat flux. Heat flux has units of power per area, or watts per meter squared in SI units. That can be rewritten as joules per meter seconds. Okay? So it is energy per area per time. Okay? Those are the units of the heat flux. Now, when we consider mass flux, there's an analogous relationship that looks similar to the heat flux that we can write down. So the analogous version of the flux for masses, or species masses, should have units of kilograms per area per time. In other words, mass of some chemical species inside some space divided by the cross-sectional area of that species fluxing through some area per time. So you're picking up a trend here. For heat flux, you have the conserved quantity, which is energy, divided by area per time. For mass flux, we have the conserved quantity, mass, per area per time. Again, energy and mass are conserved species, right? There's conservation of energy, conservation of mass. So in general, whenever there's a term flux, it's almost always defined like the following. Flux is some stuff some conserved stuff per area per time. So mass flux just follows this convention of flux being conserved quantity of mass per area per time. Now let's make things concrete. Suppose that in our material, there's some kind of chemical species that we're going to call A. Suppose you have some chemical species, for example, salt or any reactant product that you can think of. We're going to call that species A, and that's inside this material. And we want to understand how that species A, its mass, fluxes through a cross-section of this material. Now, in analogy with Fourier's relation, you kind of can guess how that mass flux may look like. Suppose you wanted to measure the mass flux of some chemical species across some material, similar to conduction. The larger the spatial gradient, if I have 10 kilograms of salt here and 0 right here, and there's a steep slope, a huge gradient of salt concentration, you would expect the flux of that salt passing across this material to be very, very large. Same argument that we made for the temperature gradient. Wow, 100 degrees up here, 0 degrees, huge energy flux coming through. Same thing with mass. So you would expect it to be proportional in some way to the slope of the concentration difference. Next, you would also expect it to be a functional, a dependence to exist on the material property. How conductive is that material to the motion of salt across that material? Just like the thermal conductivity. So a good guess for the constitutive relation that connects the flux J to the concentration of chemical species is the following. Just like this. So we have the flux J of the species A, so chemical concentration C sub A. Partial Ca, partial X is the gradient, how steep that concentration profile is across space. Just like partial temperature, partial X, but just in concentration, you're swapping from temperature to concentration. And there's a proportionality factor called D, diffusivity coefficient. This is called the diffusivity or the diffusion coefficient. Now, it tells you how conductive, how easily the salt species A can pass through that material, just like the thermal conductivity K. And again, we have, by sign convention, a negative sign out in front because a mass flux goes down a concentration gradient. So if the slope is negative, therefore the mass flux is going in that direction. To cancel that negative, we put a negative sign out in front. So you get a net positive flux of species going down a concentration gradient. Again, just a sign convention. So it turns out that this is called Fick's law of diffusion. Again, not really a law, Fick's constitutive relation. And it's identical to the Fourier's relation. Now, there is a third relationship that is very famous for momentum balance. So we have energy, mass. The third conserved quantity that we often deal with in science and engineering is momentum. There, the variable that we're solving for is not temperature, not concentration, but it's instead momentum, which usually is written as the velocity field. So in the field of fluid mechanics, the simplest relationship between the flux and your conserved species is called a Newtonian relationship or Newtonian constitutive relation. I wrote it in the most general form, so it's a little bit harder to see. But on the right-hand side, you'll have a gradient of the velocity, similar to the gradient of the concentration. The proportionality constant is called the viscosity. How hard is it to shear and make a fluid flow across a material or within a material? And that is equal to the left-hand side, which is called the stress tensor. Now, fluid mechanics is really hard. It's hard for a number of different reasons. First, it's harder because generally the function you want to find is a velocity vector, which has 3 components in a 3-dimensional world, x, y, and z. In contrast, for heat flux and mass flux, the species that you're looking for is a concentration, or a temperature. It's a scalar quantity. There's no directionality to temperature. It's just a scalar quantity. You go to a point, you know the temperature at that point. In fluid mechanics, at that point, there's 3 scalar things coming out of that point, emanating, boom. So it's a vector at a particular point, which means that everything gets upgraded by 1. So now we have tensors, which are called second-order tensor, relating another second-order tensor. That's why I have 2 lines underneath. A vector, I put 1 line underneath. Tensors, second-order tensors, I put 2 lines underneath. Now, in general, this relationship that relates this, what's called a rate of strain tensor, to the stress tensor can be related by a 4th-order tensor. So generally, this thing that comes here is actually 4 lines underneath a 4th-order tensor. It gets into details at this point, so we're not going to pursue this further. But fluid mechanics is just hard for just mathematical difficulty. Everything gets upgraded, and now you're working with vectors instead of scalars, tensors instead of vectors. So already it's harder. Mathematically, it's harder. Also, conceptually, it's harder too, because unlike energy and mass, this relationship for the flux oftentimes does not follow this Newtonian simple linear gradient relationship. So a lot of times this is not satisfied, and you get highly non-linear relationships between the right-hand side here and the left-hand side. It would be analogous to having the right-hand side here not just be proportional to partial t partial x, but quadratics or cube roots of that, or t squared. Very highly nonlinear, complicated couplings of temperature and its gradient. And that's why fluid mechanics is hard for a million different reasons. There's more other reasons too, but this is the entire field of what's called complex fluids in rheology. Okay, that was an aside. Here are the 3 different fields in my discipline of chemical engineering. This is the bread and butter of chemical engineering. This is what we solve in our discipline. Okay, so now that we know a little bit about the relationship between the chemical species of salt, C sub A, and the mass flux, we can solve our very famous and favorite equation of in minus out plus generation equals accumulation. Let's do that. So here's our favorite equation, in minus out plus generation equals accumulation. For the case of the mass transfer, this overall should have units of mass per time. So in SI units, kilograms per second. Okay. Let's make a couple of approximations. First, the generation term. In this particular case, we're working on chemical species A just diffusing inside this material, and therefore there's going to be no chemical reaction of A going to a product. If you did have a chemical reaction of some reactant A going to a product P, then this is where it would enter. You would need to include a rate law that tells you how chemical species A is being converted into products. You need a rate equation. This is the field of chemical kinetics and catalysis. Again, bread and butter of chemical engineering. Now, let's write down our in minus out because we already figured out that we know what the flux is. So let's write that down. Okay. So in minus out is simply the mass flux of the chemical species A at the x face minus out the x plus dx face. So this will correspond to flux in, J, flux out, also J, at the 2 ends of the slab, the shell, and of course multiplied against the cross-sectional area. Of course, the mass that's actually transferred across depends on the cross-sectional area. Look at this definition. Mass flux is mass per area per time. So the bigger the area, the more mass that's being transported. Therefore, when you multiply the flux with the area, you get overall units of mass per time, which checks out with our overall units of this mass balance of kilograms per second, mass per time. Now, the accumulation term on the right-hand side says how much mass of salt is accumulating inside this small little shell. That's very easy. That is simply the time rate of change of the mass of species A, of salt, inside that shell. Again, kilograms per time. The units check out. Okay, so at this point, we can use Fick's constitutive relation, put it into these mass fluxes, and simplify. So all I've done here is to plug in Fick's first law, or Fick's constitutive relation, over here on both terms. The negative of diffusivity times partial Ca partial x at the x face and at x plus dx face. Now, the right-hand side, the mass of A inside the shell. That can very easily be determined using the concentration relation and the volume inside the shell. So the mass inside that small little shell can be rewritten as the mass of A inside that volume, dV, times the volume element dV. Well, this here, mass of A divided by the volume, is the definition of our concentration of species A, C sub A. And dV can be written as the cross-sectional area A times this small increment dx. Just like that. So now the areas cancel on both ends, and we can simplify. All I've done here is to bring the small increment dx over onto the left-hand side, cancel the areas, and flip them so that we have the out face minus the in face, and factored out the diffusion coefficient d. Now, you probably remember this from the heat equation and how we derive the heat transfer equation. But this quantity right here, again, is the definition of the derivative as dx element goes smaller and smaller and smaller to a continuum point. That is the definition of the derivative as dx goes to 0. And therefore, just cleaning up, we have our final expression for mass transfer. So we just arrive at this equation. Does this look familiar to you? I hope it does, because it is identical to the heat equation. It is identical to the heat equation. It's oftentimes called the diffusion equation. So a lot of times people use them interchangeably. They'll say blah, 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 oh, I just solved the heat equation, or blah, 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 I just solved the diffusion equation. And they'll oftentimes use it interchangeably. The heat equation, on more general terms, isn't limited to energy conservation and heat fluxes. People use, oh, I solved the heat equation as a generic mathematical terminology to say they solved an equation that looked something like this. And you can see the mapping clearly, because in the heat equation, we had D here swapped with alpha, the thermal diffusivity, with the same units, length squared over time. And then we had temperature instead of concentration. But mathematically, because we're dealing with the same equation, you just swapped some letters with another letter, the solution procedure is the same. So everything you've learned about heat transfer solution for the last couple of weeks still applies for mass transfer. Zero difference. From a mathematical standpoint, everything you learn directly applies. And that's why it's so convenient that we've learned all the tools for energy conservation and heat transfer just applies directly to mass transfer. Now, in this derivation, we've made a couple of approximations. For example, the fact that there are no chemical reactions happening inside the system, but also there are no fluid motion happening inside. So the material is stagnant in the sense that there's no fluid motion sloshing salt across the material. If you do, you have to add an extra convective term inside of here, but right now this is pure diffusion, similar to conduction of heat. We have salt inside, for example, a solid material, and it's just hopping from one vacant site to another. That's diffusion. In a fluid, you can also have diffusive processes when there's no fluid motion. The salt can hop around due to a process called Brownian motion, and you would still have the same equation as you see here, even if it were not a solid material, but a fluid that is at rest. All right, and the details will change if you have fluid mechanics inside the system. If you had fluid motion happening inside this material, then you have to couple it to a momentum balance, because you need to solve for the velocity profile coupled to the concentration profile. The same is true for the heat equation. If you had some kind of energy transfer with fluid sloshing around, you need to solve the momentum balance for the velocity field coupled to the energy balance as well. All right, so this is great news for us, because with the same equations, we can use the same tools. The same equations, the same math. Now, I'd like to take a moment to describe the different types of ODEs and PDEs that we might find in engineering. Let's do that next. Now that we've derived the mass transfer equation, I wanted to take a moment to briefly talk about the essential partial differential equations in my case, the discipline of chemical engineering. But actually, the essential PDEs are more broadly applicable for other fields of science and engineering as well. I've broken it down into an energy, species mass, and momentum, in my case, fluids, but this is also true for solids as well. Let's write down the basic PDE equation for each of these, starting with the energy balance. The heat transfer equation, or the energy balance, in one form might look something like this. We have different types of terms in this expression. First, we have an accumulation term on the left-hand side that tells you how much energy is accumulating inside your control volume as a function of time. On the right-hand side, we already showed you that there's a conduction term, which came from Fourier's law, or constitutive equation, for conduction. So this term on the left and the first term on the right, this would give you what we solved as the heat equation. Now, early in the shell balance for the heat transfer equation, we also said that there could be a generation term. For example, an electrical wire running through your material could be a source of heat, or an exothermic, endothermic chemical reaction could generate heat and release it into your material. You could also have friction of a fluid. When a fluid flows and it creates shears, just as when you rub your hands warm up, it's generating heat as friction of fluids rub past each other. It would also appear in this generation term. Now, there's one term that we haven't talked about yet in this class, which is a convection term. That's what I've written here, C-O-N-V, convection. This term is the velocity vector of a fluid flowing dotted into a gradient of your temperature. So grad T, gradient of a scalar, will be a vector. It's dotted into a velocity vector. And so the dot product would be a scalar quantity. And it will tell you how much energy is passing through your system due to motion of a fluid that's advecting or convecting energy across your system. This is very often the case when you have fluid systems that can have flows. In our case, we did problems of pure conduction, which was a solid slab of material. There's no motion of the fluid molecules inside the system. It's a solid piece of material. That's why we ignored this convection term. We also said there was no generation, and so we only had the first term on the left and the first term on the right, and that was our heat equation. Now, this energy balance is not written in the most general form. For example, we've assumed a constant density. We've assumed a constant thermal conductivity. If you want to generalize that, you have to go one step up and see where those terms go if you don't make these assumptions. But really what I wanted to show you here is that you have these four terms, accumulation, convection, conduction, generation, that forms the basic structure of the energy balance. Moving on to the mass transfer equation, as we just derived using the shell balance. It will look something like this. Again, let's label each term. Once again, it's the same four categories of accumulation of some salt or some chemical species A inside your control volume. Second term here, convection. You can have fluid flowing that convects your species along your control volume, just the same way you can convect energy across your system. Right-hand side, we have diffusion, molecular diffusion of little solute species moving along your system due to thermal diffusion. Not convection of bulk material flowing, but of random hopping of species across your material. This can happen in a solid piece of material. You have diffusion of hopping of molecules from one site to another inside of a crystalline solid material. That can happen. Lastly, we have a generation term, R sub A, is a rate of reaction. This is particularly important for species mass balance in the field of chemical engineering and catalysis and chemistry, because we are all about solving diffusion, convection, reacting systems. So this would be like some reactants reacting and becoming products. This is where all the chemistry would be put in here to this term right there. So that also is obvious. You have generation or sinks of reactant of species A if it's becoming products, right? So we need to include a generation term. But morally, it's the same for classification, accumulation, convection, conduction or diffusion of some sort that seems to blur out variation in your density or variation in your temperature profile. Lastly, some generation of species mass, some generation of energy. Lastly, let's talk about the momentum balance. In this case, I'm going to write the fluid momentum balance. It would look like this. Let's classify each term. It would be these classifications. Accumulation of momentum inside your control volume, convection of velocity gradients inside your fluid system. You have a viscosity, which is a material property of, in this case, a Newtonian fluid, and diffusion of momentum. Lastly, we have some source of forcing, some pressure gradient that can generate momentum and motion of fluid inside your system. So same for classification of accumulation, convection, diffusion, pressure generation, or some kind of generation. This basic structure is true for any conservation equation. I think for various areas of science and engineering, you're going to have this basic structure. Of course, the details of the terms will be different across the different fields and different disciplines, but more or less, this is going to be your basic structure. In minus out plus generation equal accumulation will give you this basic structure for your conserved quantity. Now, I wanted to talk a little bit about this momentum balance in the fluids because it's a little bit weird. First of all, notice that this is a scalar quantity. Every term in here is just a single scalar point. If you go to some location in your material or your fluid, there is a temperature, a scalar, a number, 100 degrees C at that point in that space. Same with the concentration. There's 1 kilogram per meter cubed of some chemical species at a particular point inside your material. Here, this is not a scalar. This is a vector quantity. I'm taking a gradient of a scalar. This is a vector. Here's a vector as well because I'm taking a Laplacian of a vector. The underline underneath, the V, means it's a vector. Okay? Same thing over here. These are vector quantity. This term right here, V dot grad V. It's a weird term. This is the term that generates turbulence. This is the term that gives a lot of people jobs in fluid mechanics for decades. Without this term, this equation would be linear and the world would be very different from how we know it today. It would be boring in a mathematical sense because linear dynamics don't really give amazing results. You have one input that doesn't compound in weird ways. But when you have a nonlinear term, which now you guys know how to identify nonlinear terms because this is the function you want v multiplied against the gradient of itself, so that's a parabolic quadratic term, and therefore this is a nonlinearity in the partial differential equation. And nonlinearity means you put up an input of one thing and it becomes turbulent and chaotic and you can't predict where that particle will go as a function of time. It's chaos, complete chaos. Chaos in the mathematical sense. You cannot predict where that trajectory will go as a function of time. And small little minor deviations in your initial condition will result in very, very drastically different outcomes in trajectory space. This is called, there's a thing called a Lyapunov exponent that tells you how chaotic the system is. What you do is you have some initial condition, you let that initial condition evolve as a function of time, and you see where it ends up. And you make a small little epsilon deviation and see where that ends up. If it's a linear system, it will always end up with the same epsilon deviation you put in initially at the end. It's a very predictable dynamics that you can predict. Okay? But with a nonlinearity, everything goes crazy, chaotic, and turbulent. Now, mathematically, also something weird. I have a vector dotted into a gradient of a vector. Hold on. You guys know how to take the divergence of a vector. Well, first of all, let's define some things. So we have a vector, v. And this vector is going to point along some three-dimensional space. It's going to have three components in a 3D world: Vx, Vy, and Vz. It's going to tell me at that continuum point inside of my material, how much is it going up, how much is it going to the side and to the other side. That's a vector quantity. Now, you guys have learned from your previous vector classes how to take a divergence of a vector. No problem. That's just the sum of the partial derivatives. That's the divergence. And you know that because the gradient operator is just a row vector of the derivatives. Just like that. So you have partial x, partial y, partial z as a row vector. You go to each element and you do a matrix summation. That's what you've learned from your linear algebra class and your knowledge about vectors. This ain't that. This gradient of the velocity is not a dot product. This is a gradient of another vector. This is a dyad. So the gradient operator is not a row vector, it's a column vector. So you're taking the dyadic product or an outer product of two vectors. What is this? Is it making you nauseous? It's making my brain explode. This turns into a matrix, also called a second-order tensor. You get a matrix to come out. You get a 3x3 matrix. So you take each component, take the derivative, put it in one entry of your matrix. You take the next one, multiply it, and then put it in another entry of the matrix, and so on and so forth. Okay? So it turns out that a divergence, this is called a divergence of a vector, is just a sum along the diagonal. So you take partial Vx, partial x, partial Vy, partial y, partial Vz, partial z, that is the sum. So the trace of this matrix, the trace is defined as the sum of the diagonals, gives you the divergence. This is a scalar quantity. This is a scalar quantity up here. This gives you a matrix or a tensor. Just like that. So this is why fluid mechanics is so hard. Mathematically, you have to deal with second-order tensors. You have to deal with things like gradient of a velocity, and then all of a sudden it becomes this second-rank tensor. In any case, you guys don't have to worry about a lot of this stuff for knowing the basics of energy, species, mass, and momentum balance, but I just wanted to give you a glimpse of how people in the research community use applied math and details of mathematics of vectors, tensors, partial differential equations, combine that knowledge together to solve a really hard problem like fluid mechanics. All right, let's end here as motivation for all the really cool upcoming courses that you might take in the future related to energy, mass, and momentum. And by the way, these are each separate courses. There's an entire class on energy balances. There's an entire class on kinetics, reaction engineering, and catalysis that deals with species mass balance, about effectiveness parameters, Thiele moduli of diffusion reaction problems. That's all here. There are tens of classes on just this equation. There's an entire class on just this term of this equation. There's an entire bunches of classes of different versions of this where it's not a Newtonian fluid like this one, but for a viscoelastic non-Newtonian complex fluid. There is so many cool problems out there in science and engineering, and you need to know the language of math to be able to speak these problems. Once again, math is kind of like a foreign language. You have to practice to get better at speaking the language, and only after you can speak the language, you can apply these problems in real problems in science and engineering. All right, I hope you have a nice day. I will see you next time. Bye.